Today we are going to discuss about the how to derive the shear force diagram from the load diagram and bending moment diagram. Also, if you know the bending moment diagram, how to derive back from the bending moment diagram to shear force and the shear force to load diagram, so we can understand easily how what is the relationship between the shear force bending moment diagrams and load diagrams. So let's consider a simply supported beam which is supported one end on the pinned support and another end on the roller support, which is subject to a uniformly distributed load of 20 kilonewton per meter, and the span length is 10 meter. If we consider a free body diagram for this arrangement, here it can take the vertical reaction as well as horizontal reaction, and this can take only the vertical reactions. Since it is a pinned, it cannot take any moment. So if there is no horizontal load, if we apply the equilibrium equation for this free body diagram, this horizontal component will be 0 since there is no horizontal load, and due to this vertical loading, so each support going to have the same reaction of 100 kilonewton. Since this 20 into 10 total load is 200 kilonewton, since this is a symmetrical loading, so it's going to have the 100 kilonewton each. If you see the shear force diagram, it's going to be the reaction 100 kilonewton going up, and after that the uniformly load linearly it is decreasing and coming to minus 100 kilonewton, and again here there will be support, it will reach to 0. So in this graph what we are saying is that this is the in kilonewton this is shear force, and in x-axis what we are saying is the span 0 meter, 2 meter, 4 meter, 6 meter, 8 meter, 10 meter. Same way in bending moment diagram also. So whatever we are seeing here is the bending moment value in kilonewton meter, and this is the span length. So at the support it is having 0 value, and maximum somewhere in 5 meter, exactly at the mid span it's having the maximum value. So this how to calculate this value, how these all are it's very basic, it's everybody knows, so I'm not going to spend any time on this. Now let's compare all the three together and what is the relationship between all these three, and how to derive this shear force from this bending moment diagram. If you know the shear force diagram, then what would be the load diagram for this particular case, that we will discuss in detail. Let's consider any two section. Say example, I am taking 1 meter and 2 meter. So between this 1 meter and 2 meter, if you see the bending moment diagrams like varying like this, and the difference here the value is 90 kilonewton meter, and here 160 kilonewton meter, the difference is 70 kilonewton meter. So what it is telling us is like if the bending moment is changing, so the difference between these two is equal to the shear force between these two sections. So the shear between these two sections, if we take area of this shaded portion, it will be equal to the shear between these two sections. So the gap is 1 meter, and here the value is 80 and here the 60. So if we take the average, it is 70 into 1 meter, which is equal to 70. So it is exactly matching between the difference between these two values. If you take any section here, difference between these two values is 160 and 210, it is equal to 50. If you see here the 40 and 60, so the average is 50. 50 into 1 meter, 50. So if you take any interval, exactly it will match with the shear force, the difference in moment which is equal to shear force. Same way the difference in shear force will be equal to the loading total load act between these two sections. Say example, here the difference is 80 and 60, the difference is 20 kilonewton. This is 1 meter, so 1 into 20 equal to 20, so it is exactly matching. So the difference is constant, which means the slope is constant, so the loading will be uniform. Here the slope is non-uniform, so the shear is varying. It is the shear is not constant. If you take the shear force first 1 meter, it will be very high, and if you take somewhere here, so it will be very less. That is how here the difference in moment is too high. The difference here, if you see 240 and 250, only 10, so it's very less. So if we consider another case where the same beam subject to one point load made 5 meter, so the reaction would be 50 kilonewton, and the shear force diagram will be like this. 50, and it will be, there is no load between this point and this point, so it will be constant. Again the 50 minus 100, it will go to minus 50, so it will be again constant, and when reaches here, so again this 50 will take it to 0. Same way, if you draw the bending moment diagram, so it will be like this. So now if you see the difference here again, so the 1 meter and 2 meter interval, so 50 and 100, the difference is 50. Here if you take 1 meter into 50, 150, so the difference in moment is exactly matching with the shear force between the two section. Same way here, if you see, there is no difference, so there is no loading between these two section. So here if you see, the slope is constant, here the load is uniform, here the moment is, the slope of the moment diagram is constant, so the shear force is uniform. There is no difference in shear force, and there is no loading between this section. So that is the relationship between the all these three: load diagram, shear force diagram, and bending moment diagram. Now come to the summary. So the rate of change of bending moment, which is called the shear force. The same way, a rate of change of the shear force diagram will be equal to the load diagram of the particular structure.